Disc and a hoop. They have the same, very close, if not the same width. Their masses are pretty close. I mean, they feel like they weigh about the same. The radii are the same. But we're going to have a race. I'm going to put them at the top of the incline, let them go from rest. What do you think is going to happen? Get it there at the same time?
No.
Okay. So we have some votes for the same time, some votes for not the same time. For those of you who don't think the same time, why not? We'll have different moments of inertia. Well, let's see. This guy won. This guy will always win. If they have the same mass and the same radius, though, why are their moments of inertia different?
The mass is concentrated to the edges of the radius.
Exactly. For the hoop, the mass is concentrated on the outside edge. So all the mass is a greater distance away from the rotation axis here. Here, the mass is distributed uniformly throughout the whole entire disk. So we have mass that's close to the rotation axis, some mass that's far from the rotation axis. But on average, the mass is closer to the rotation axis for this guy. That means its moment of inertia is smaller. Smaller moment of inertia will result in a greater angular acceleration for any given torque. By the way, which of the forces that are actually acting on these is causing it to roll?
Friction on the track.
Friction on the track. Exactly right. If there was no friction, and I put this down, it would simply slide down the incline. Friction is required to make it roll. Friction acts on the outside edge. The rotation axis is in the center. The lever arm is the radius of the disk. So the lever arm times the force of friction gives us a torque. Okay. Now the symbol we use for moment of inertia is a capital I. So basically, Newton's second law, the left-hand side is simply the net torque acting on the object. If you sum up all the radii and their forces, you get the net torque. That has to equal the moment of inertia of your object times the angular acceleration of your object. Okay? This is Newton's second law. But this is Newton's second law as applied to rotation. Okay? So you have to have a net torque if you want to make your object start rotating if it's at rest. Or if it's already rotating and you want it to slow down and come to rest, you need the net torque. I is mr squared only if all of the mass is a distance of r from the rotation axis. So mr squared, this is mr squared. All of the mass is a distance of r away from the rotation axis. This hoop isn't thick enough to make it, to worry about the inside being closer than the outside. You'd have to have a pretty thick region to have to worry about the extra distance. So mr squared, in and of itself, is only valid for hoops and for point masses. Now by point masses, I mean the object is small compared to the radius that it's moving through. For example, the moon orbiting the Earth. You could treat the moon as a point mass in relation to how far away it is from the Earth. Now the moon is a big object, But if all we're trying to look at is its rotation around the Earth, then the distance between the Moon and the Earth is incredibly huge compared to the size of the Moon. So mr squared would work for the Moon orbiting the Earth. It would work for the planets orbiting the Sun. Okay? It will work if we had, say, a yo-yo on a string, where the string was incredibly light and the mass of the yo-yo was significant. Now, all objects have a moment of inertia. They don't have to be moving to have a moment of inertia. This has a moment of inertia of mr squared through this axis, whether it's moving or not. Okay? So inertia is something it possesses just for the fact that it exists. Okay? Moment of inertia of this guy is going to be smaller than mr squared. And to figure it out, you'd have to integrate. You'd have to integrate all the little dm's, treat it as a whole bunch of little tiny point masses, and integrate its distance squared from the origin, from the rotation axis. And again, since Calc 2 is not a prerequisite for this class, I'm not going to make you integrate for it. Well, that's not entirely true. Your computer problem 3 does an integral, but we give you the integral to integrate. So you don't have to figure out the integral yourself. For objects such as our disk, sorry, I got to borrow a book. That's okay. Where are you? There we go. Table 12.2 on page 347. So table 12.2 on page 347, the authors have very kindly done the integrals for us. And it shows us, or tells us rather, the moment of inertia of, say, a cylinder, a disk, through its rotation axis. So if you look on the table, you look for a disk or cylinder. This is a cylinder, it's just short, but it is a cylinder. Look for the disk, the solid one. It shows you an axis going through the center. What's the moment of inertia? 1/2 mr squared. Exactly right. So you don't have to integrate. They've told us. I for this guy is 1/2 mr squared. So we're good. It shows you for a sphere as well. So like a bowling ball or a spherical shell, it gives you as well. It gives you thin rods. It tells you the moment of inertia of 8 different objects. So plan on using the table. Okay, there's a similar table in the test notes. The test notes don't have the picture though. It just tells you that the solid cylinder, like the disk, is 1/2 mr squared through its center, and so forth. So I is mr squared only for hoops and point masses. Table 12.2 gives us equations for the moment of inertia of some other objects. There's one other situation we might run into. For example, let's say we took the hoop here. Instead of, say, rolling it down the hill, instead, let's say I held it on the outside edge. If I held it on the outside edge, it would rotate. Torque due to gravity would pull it down. But the moment of inertia is going to be different because the rotation axis. If it's rotating about my fingers, the rotation axis is right here. That's not right here. The one on the table is right here. We need to know how to find the rotation axis if I move, to find the moment of inertia if I move the rotation axis. We have a nice little equation that we can use. Notice this rotation axis about my fingers is parallel to the one that goes through the center. We have what's called the parallel axis theorem. That's one other way that we're going to find moments of inertia. as the name implies, this equation only works to find the moment of inertia around an axis that's parallel to the one that goes through the center of mass. Okay? The moment of inertia. Number one, do you expect it to be bigger or smaller with my out on the outside edge here compared to the one that was in the middle? Bigger. The mass, on average, is now located even further away from the rotation axis. So the moment of inertia will be bigger. To find the moment of inertia around that new axis, we simply need to take the moment of inertia that passes through, the moment of inertia that is through the center of mass, so the one off the table, plus the mass of the object times d squared. D is the distance between the new rotation axis and the center of mass. So here's our hoop. Here's our new rotation axis. D is the distance between our new rotation axis and where the center of mass is located. So in this case, in the example of holding the hoop out at the outside edge, D would be R, the radius of the actual hoop. So the moment of inertia about that point would be the mr squared, which is the one that we get through the center of mass, plus md squared, but d is r in this case. So I, in this particular example, would be 2mr squared. Be twice as big, actually, than it was before. What would be different if I was holding the outside edge of the disk, the solid one? What in this equation would change? The one through the center of mass would be 1/2 mr squared, but d would still be r. So we'd have 1/2 mr squared plus mr squared, so we get 3/2 mr squared. So these are the three ways to find moment of inertia. If all of the mass is located at the same distance away from the rotation axis, you can find moment of inertia this way. This equation, the mr squared, applies as long as the size of the object is small compared to the radius that it's going to move through. Table 12.2, you'll use parallel axis theorem. So 3 ways to find moment of inertia. If one of those ways doesn't work, then you're going to have to know something about angular acceleration and torque and find it through this equation.